Now we're going to work some problems in section B of the student packet that have to do with acceleration due to gravity, or lowercase g. So be careful to see what the problem is asking you for. In problem 3, it talks about how many people think that when astronauts get in orbit above Earth, like if they go up in the space shuttle, that they're above gravity, or that they're in a totally weightless environment. And so we're going to check to see if that's true or not. So it says calculate g. So that tells you we want to know the acceleration due to gravity, not the gravitational force. So whenever something is asking you for acceleration due to gravity, that is the universal gravitational constant times the big mass, right? Divided by the distance from that mass, from the center of that mass, squared. So here, for something that's at the space shuttle height, the r would be the radius of the Earth plus the altitude of the space shuttle. And remember, we need to work in, that's 6.4 e to the 6. We need to work all in meters. So the Earth's radius is 6.4 e to the 6th. The space shuttle is at an altitude of 200 kilometers, but we have to multiply by 1,000, so that's 200,000 meters. And so that gives us 6.6 e to the 6th meters as the r. Okay, so big G is 6.67 e to the negative 11th. The Earth's mass is 6 times 10 to the 24th. And then we divide by the square of the distance to the center of that big mass. And so that would be 6.6 e to the 6th, and we square it. Okay. And so we find that at the height of the space shuttle, the acceleration due to gravity is 9.187 meters per second squared. Part B says, what percentage is that of the acceleration due to gravity near the surface of the Earth? So 9.187, which is g at the height of the space shuttle, divided by 9.8, which is g close to the surface of the Earth, is 93.75%. So even when you're as far away from the center of the Earth as the space shuttle, you're not in a totally weightless environment. The acceleration due to gravity there is still 93.75% as large as it is near the surface of the Earth. Let's also look at the next problem, number 4. Here it's talking about a space probe in orbit around Mars. And so first we want to know, what is the acceleration due to gravity, right? Not the gravitational force, but g, acceleration due to gravity, at the location of the space probe. So this is, the g at the orbit of the space probe. And it's going to be the universal gravitational constant times the big mass divided by the distance from the orbit to the center of that big mass squared. So here, the r is going to be the radius of Mars plus the altitude. And so that will be, we've got a megameter here. Remember, mega means 10 to the 6th. So we've got the radius of Mars is 3.39 e to the 6th meters plus the altitude, and they gave that to us in kilometers, we have to make that meters as well, plus 300,000 gives us that R. And so the R here is 3.69 e to the 6th meters. Okay, so at the altitude of that space probe, the acceleration due to gravity would be sure here to use the mass of Mars. That's the big mass, not the mass of the space probe. And we get that the acceleration due to gravity at that location is 3.130 meters per second squared. Then it asks, what about the acceleration due to gravity near the surface of Mars? So this is the G near the surface. It's the same formula, but our R is going to be different, right? At the surface of Mars, the R is just the radius of Mars. So we're going to get a larger acceleration due to gravity. Of 3.709 meters per second squared. Okay. Part C says, how much does the space probe weigh in its orbit above Mars? Now, we could use the law of gravitation, which says that force of gravity is G, big mass times small mass, divided by the distance squared. But now that we know the acceleration due to gravity, the lowercase g at that location, remember that the force of gravity equals the mass times the acceleration due to gravity at that location. So I know the mass of the spacecraft is 439 kilograms, and I already know g, where it is on orbit. That's 3.13, and so I can just multiply those. And I get that at its location in orbit, it has a weight of 1374.1 newtons. But then it says, what if the space probe landed on Mars? So it would be on the surface of Mars. Then its weight, its force of gravity, would be its mass times g on the surface. Right? Mass is constant everywhere, but weight depends on where something is. So here, 439 times 3.709. So it's going to be heavier on the surface, and it will have a weight of 1628.251 newtons.